Hi you guys. This video is going to cover two different types of problems. The first type is I'm going to throw limiting reactants into the mix. So I'll have two problems where I show you how to do a solution stoichiometry problem where there's a limiting reactant. And then the last two problems, I'm asking you to find the number of milliliters in one of the reactants. And this one kind of has a twist. So yeah, 4 problems, 2 of one type, 2 of another type. So the first thing you're going to have to do, of course, is, yeah, you guessed it, write a balanced chemical equation. And I'm just going to throw that up there for you. I am going to be asking you to make sure that you have all of the states of matter indicated in each one. And this is really important because of that one. You're going to need to know who your precipitate is. These are always going to be double displacement reactions. We'll have 2 types. The first type is just a basic precipitation, salt. It gives you a solid and another salt or something else. The second types of problems we'll be doing, not today, is an acid base, leaving you with salt and water as your products, but not today. Again, they'll all be double displacement reactions. So we want to know the grams of this, and I like to write out what I have under each chemical. So in this case, I have 150 milliliters of a 0.5 molar solution, and here's 100 milliliters of a 0.4 molar solution. As you can see, they've given us amounts of both reactants. Nobody's in excess, so how are we going to figure out? Well, if you guessed go to moles, you got it right. Okay, so let's start with the silver nitrate. So we have 0.5 moles of silver nitrate. Draw my line. Per 1 liter, because that's what's in there, moles per liter. And I'm going to go ahead and convert milliliters straight to liters in my head by moving the decimal point 3 places. So 0.15 liters. And I already worked it out, so I'm going to go ahead and just look at my paper. 0.075 moles of silver nitrate. Now let's do the potassium chromate. We have 0.4 moles, yes, that's a 0, of potassium chromate per 1 liter. And then go ahead and convert milliliters to liters by moving the decimal. 0.04 moles of potassium chromate. Now this is what I have. It doesn't tell me the limiting reactant yet. In order to figure out the limiting reactant, I'm going to have to do a mole ratio. So I guess if we were to write steps for this, step 1, find the moles of each reactant. Then step 2 is going to be do the mole ratio. So we'll do that step, ratio. So we'll do that step now. I'm just going to use potassium chromate because this number is still hanging out in my calculator. In this case, I could do that one in my head, but usually that's the one hanging out. According to the balanced equation, for every 1 mole, you see there's that 1 there, of potassium chromate, I have 2 moles of silver nitrate. Which gives me 0.08 moles, that's an 8, come on, of silver nitrate. And what's that word we need? Needed. So if I compare this amount to this amount, I can see that I need a lot more than I actually have. Therefore, I'm going to run out of the silver nitrate. The silver nitrate becomes my limiting reactant. So since I happen to have 0.075 moles of silver nitrate, I can use that to find the grams. And I don't care about the potassium chromate anymore. That one is in excess. Okay, so 0.075 moles of silver nitrate. Drawing a straight line is seriously an art form. We have 2 moles of silver nitrate for every 1 mole of silver chromate. And to get to grams, you're going to use the molar mass. And so 1 mole of silver chromate. If you want to pause the video and see if you can come up with the correct molar mass, feel free. Otherwise, I'm just going to put it on here as 332 grams of silver chromate. And that gives me an overall mass of 12.5 grams of silver chromate. If you need more time to write that down, feel free to pause. I'm going to do another problem that is exactly like the last one we just did. If you want to pause the video and see how you do with it, feel free. Otherwise, I'm just going to go ahead and plow forward. Again, here's your balanced equation. This is the precipitate we're after, and the question says how many grams. So I'm going to write grams here. I know that I have 25 milliliters of a 0.350 molar solution. And then for the copper 2 sulfate, I have 45 milliliters of a 0.125 molar solution. Now that the inventory is over with, let's find step 1. I don't think I put a step 3 on the last one, but step 3 would be find the grams of the precipitate. Okay, so step 1 is to find the moles of each reactant. So we have 0.350 moles per liter. I should have written the sodium hydroxide here. That goes right there. And then I'm going to convert milliliters to liters by moving the decimal place 3 places. So that's 0.025 liters. And that ends up with 0.00563. No, it doesn't. I can't read my own writing. Let's erase that. Try it again. 0.00875 moles of sodium hydroxide. Doing the same thing for the copper 2 sulfate, 0.125 moles of CuSO4, remembered at that time, per 1 liter, because that's what's in the big M. Converting milliliters to liters by moving the decimal 3 places, 0.45 liters. And that gives us 0.00563. There's where that number goes. Moles of copper 2 sulfate. Next step. Well, if you guessed find the limiting reactant, you're right. We have to do the mole ratio to do that. So 0.00563 moles of copper sulfate. And from the balanced equation, we have 1 mole of copper sulfate to 2 moles of sodium hydroxide. Punching that into the calculator, you'll find where I actually wrote it. 0.0113 moles of sodium hydroxide needed. If I compare the number I just wrote in blue to this number, you can see that I'm not going to have enough sodium hydroxide. Therefore, the sodium hydroxide is my limiting reactant. So since I know the sodium hydroxide is the limiting reactant and I have 0.00875 moles of it, I can use it to find the grams. 0.00875 moles of sodium hydroxide for every 2 moles of sodium hydroxide. We have 1 mole of copper 2 hydroxide. To get to grams, I'm going to need the molar mass. So for every 1 mole of copper hydroxide, then I'm going to have a molar mass, I wrote it down, of 98 grams. So you punch that into your calculator, you pay attention to sig figs, and you end up with 429 grams of copper 2 hydroxide. This one has a lot more twists and turns than the last one. Of course, you're going to need a balanced equation, so if you want to pause the video and try that before I reveal it, feel free. I'll give you a second to hit pause. Okay, there's your equation. The question is, how many milliliters of barium nitrate? So I'm after milliliters here. I've been given 0.280 moles of this. And the question is, I need to precipitate all of the sulfate ions in this. So I want all of this. This is automatically my limiting reactant because I want all of that to go into there. And I truly don't care about the limiting reactant at this point because I'm not going to then later find the grams of barium sulfate. But the point is, I need all of the sulfate ions gone. And where do I find the sulfate ions? I find them in the aluminum sulfate. And I happen to have 25 milliliters of a 0.350 molar solution. If I look at aluminum sulfate, what it's actually doing in the water, and if you recall, I had you draw some pictures of these reactions. And we know that the aluminum, if I dissociate this salt, we know the aluminum is actually going to look like this. Well, no, not quite like that. There we go. Now if I use these two numbers to find the moles, that's going to be the moles of aluminum sulfate. So go ahead and pause the video and see if you can come up with the number of moles from aluminum sulfate, just like we did on the last 2 problems. When I calculated that, hold on, I gotta find where I wrote it. When I calculated the amount of aluminum sulfate, I found out I had 0.00875 moles of aluminum sulfate. The question is, how many moles of sulfate ions do we actually have? So to calculate that, it's just a mole ratio. Moles of aluminum sulfate and I know that for every 1 mole of aluminum sulfate, I have 3 moles of sulfate ions. So the amount of sulfate ions I end up with is 0.0263 moles of sulfate ions. Those are all of the ions that I need to use up in this reaction. So how many milliliters of barium nitrate am I going to need to get all of these sulfate ions gone? And to do that, I do need to look at the precipitate. The precipitate is barium sulfate. So I know that if I want to make barium sulfate, and oh yeah, lost my train of thought there for a brief moment. So I happen to know that for the sulfate ions, I have 0.0263 moles of sulfate ions. In order to make all of the sulfate ions gone, the question becomes, how many moles of barium do I need to make all of that gone? This one is a 1-to-1 mole ratio, and you can set it up if you want. I mean, it's 1-to-1. But if you actually wanted to set up the problem, it's 0.0263 moles of barium ions. No, it's not. I clearly need more coffee this morning. Should have done this video last night. Oh well. 0.0263 moles of sulfate ions. And I happen to know that for every 1 mole of sulfate, I have 1 mole of barium. Which then, yes, gives you 0.0263 moles of barium ions. Well, that's good, because now if I want all of the sulfate ions used up, I know I'm going to need this many moles of barium to do it. The question wants me to know how many milliliters should I add to make that happen. I know that I have 0.0263 moles of barium. And if you look at barium nitrate, when that salt dissociates, I know that if I have 0.0263 moles of barium, I can then get from barium to barium nitrate. So every 1 mole of barium gives me 1 mole of barium nitrate. Then for every 0.280 moles of barium nitrate per 1 liter, because that's what, you know, the big M is. And for every 1 liter, I need 1,000 milliliters. That was weird. We'll fix that. There we go. Well, overly fixed, but that's okay. I'm giving you a minute to process all of that. So when you run your final calculations, then you end up finding out that you need, somewhere I wrote it on my paper, maybe I didn't. Huh, interestingly enough. Yeah, I did. 93.8 milliliters of barium nitrate needed to run this reaction. Like I said, that one was going to be a lot more difficult than the first two. Let's try one more just like it. If you feel confident, feel free to pause the video, see how you did, or my suggestion to you is pause the video and see how far you can get before you get stuck. If you feel like, oh my gosh, Norton, I totally need to see you do another problem, just pause the video long enough, give yourself a chance to write out the chemical equation, and then jump back in, and I'm going to work our way through it. Okay, pen, something interesting. We'll see if that works. Okay, so what volume in milliliters of silver nitrate? So I know I need milliliters of this. I happen to have a 0.415 molar solution of it. And I have 35 milliliters of this guy and a 0.128 molar solution. The question is, how many milliliters of silver nitrate do I need to get all of the all of the bromide ions gone. They're all going to end up in there. So how many milliliters of silver nitrate do I need to make all of the bromide ions gone? Yes, the first thing you need to do is figure out the moles of bromine ions. To figure out the moles of bromine ions, you could start off just a little different than what I did last time, but not completely different. I'm just combining a couple steps. If you look at calcium bromide, we know that this salt is going to dissociate into calcium ions and bromine ions. So the question becomes, how many moles of bromide ions do I actually have so that I can make them all go away? If I know this, you can convert it to moles and then do a mole ratio between calcium bromide and the bromide ion, or you could do it in one step. Here I have 0.128 moles of calcium bromide for 1 liter of calcium bromide. Converting this, well, let's hold off on the volume for a second. I know that I have 1 mole of calcium bromide for every 2 moles of bromine. Since I just want moles of bromine in my final answer, I have to get rid of the volume. I have a liter hanging out here, and I don't want that. If I wanted to find the concentration of bromide ions before I started, then that would work, but I don't want that. I just want moles of bromine. So this is where I'm going to use this number. I'm going to convert that to liters by moving the decimal place 3 places to this way, to the left. 0.035 liters. So that makes the liters cancel, the moles of calcium bromide cancel, and I'm left with moles of bromine. So the number of moles of bromine that you end up with is 0.00896 moles of bromine. I want all of those bromine ions to go into the silver bromide. To make this salt, I know that silver ions plus bromine ions is going to equal silver bromide. I happen to have 0.00896 moles of the bromine ions. So the question becomes, how many moles of silver do I need to get all of the bromine ions into that salt? It's a 1-to-1 mole ratio. So if you said, hey, Norton, that's going to be the same amount because it's a 1-to-1 ratio, you are right. So I need 0.00896 moles of the silver. Our final part comes from this. How many milliliters of silver nitrate am I going to need to make all of those bromine ions go into the salt? I just found out that I needed 0.00896 moles of the silver nitrate to run this reaction. So we end up with a salt that dissociates in water like that. From the previous slide, I discovered I needed this many moles of silver to run the reaction. If I need that many moles of silver, then the question becomes, how many moles of the silver nitrate do I need? And then our final question is, how many milliliters? I'm going to run this all in one step. You can break it apart into multiple steps, but I know I need 0.00896 moles of silver to run this reaction. I know that for every 1 mole of silver, I need 1 mole of silver nitrate. Remember, I'm after milliliters. I'm going to use this number, 0.415 moles of silver nitrate in 1 liter. I'm after milliliters. 1 liter contains 10 to the third milliliters. Liters drop out, moles of silver nitrate drop out, moles of silver drop out. I'm left with the unit I want, which is milliliters. Using my handy-dandy calculator, I came up with 21.6 milliliters. I know this type of problem is difficult, and we are going to be doing a lot of practice with these. I encourage you to do the worksheet that is associated with the video. Let me assess it as quickly as possible, and then I'll decide how much more practice we need with these 2 types of problems. On that happy note, have a great day.